Hello, the web application we are presenting today is called Parkit, Safe and Simple. There are two members in our group, Alexander Chavez and myself, Alain Tamazian. My responsibilities included web scraping the dataset, safety score calculation, database management, and back-end programming. As the app name suggests, our project topic is a safety-focused parking assistant. Drivers can use the web app to find the best and safest parking option for them, as well as get details for a specific location. Besides the utility of making the parking process easier, our main motivation for this app was the issue of safety. As you can see from the FBI statistics on the right, parking locations like garages are one of the most high-risk environments, especially for women. Unfortunately, these statistics don't even account for the risks of walking to and from street parking, which is another common location for crimes of opportunity. Our custom safety score measures past and present risk for search locations and informs users about each parking spot's level of safety. Unfortunately, due to the time constraint, we limited the current scope of our application to LA zip codes 90028 and 90038, shown on the bottom left. Most of our data was collected by web scraping Parkopedia. Since the website is dynamic, Selenium had to be used to be able to crawl and scrape the required information. Also, as you can see right here, this is not structured data, and therefore a lot of pre-processing was required in order to format it into usable attributes. One of the key features in our project, which we did not get from Parkopedia, was the safety score. Our custom safety score is unique in that it is calculated specifically for our task of measuring parking location safety levels. Through qualitative and quantitative research, we calculated this score using subtractive formulas starting at 100. We took into account criteria like parking type, security, street activity, as well as past and current crimes. Based on our research and available crime data, all else equal, the order of safety for parking types from safest to worst is street parking, parking lot, and garage. By many in law enforcement, garages are often considered least safe due to their design, which creates an enclosed, isolated place with easy access, poor lighting, and no security. Therefore, for locations with a garage parking type, we subtract 10. If the type is a lot, we subtract 5. For security, we focus on whether the garage or lot includes human employees, such as attendants, valets, and guards, which act as deterrents to crime. In such cases, we add 5 to the safety score. Similarly, if the parking location is not on an active or main street, another 10 is subtracted. Although the images on the right are extremes, the intuition is unchanged. It is generally known that crimes of opportunity are much less likely when there is a lot of foot or car traffic, such as on a popular street like Vine, rather than a smaller remote street like Gower. Most significant to our custom scoring are calculations for past and current crime. Regarding recent crimes, daily updates from citizens are used. However, we obviously need this to reflect the current state of the parking location, so this variable will not be included as part of the static safety score that is stored in our cloud database. It will be calculated in real time upon every user query in Parkit, which I will explain shortly. Now, for the historical considerations, we created our own crime index for each location, customized to best reflect our safety interests. For this, we use the LAPD crime dataset that has a collection of all crimes that have occurred from 2020 to the present day. This is almost 500,000 instances. For our task, the most relevant columns are the crime description, premises description, and weapon description, as well as the latitude and longitude. We also use the area name for some pre-processing. We had to count all of the crimes near each location, specifically within a quarter-mile radius. Then we adjusted their weights accordingly. To not do computations for 335 times 450,000 pairs, we had to greatly reduce the size of the dataset. So this is the notebook that I used for the required pre-processing and calculations. It is included in the Google Drive folder for the code submission. Over here, we looped through for the 450,000 instances and removed those which do not match the scope's areas or zip codes, which we reverse geocoded. Once this was done, our dataset was under 33,000 incidents, as you can see over here. Finally, we could count the number of crimes that occurred in the vicinity for each parking location. We used coordinates of each crime and parking location to find their distance using the GeoPy library. Any incident that was within 0.25 miles was assigned to its corresponding parking location. Then, for every one of these locations, we applied the appropriate weights to each incident. So crimes that were related to cars or parking, such as over here, based on the description, a vehicle was stolen, or another example could be that something was stolen from the vehicle, or over here, based on the premises description, we can see the premise was a parking lot or a garage. For such cases, a ×2 multiplier is used. Additionally, if the crime that occurred was a violent crime, which obviously increases the risk to the user, we apply a ×3 multiplier. For this, we mainly look at the weapon description. Any crime that includes a weapon is a violent crime. For example, over here, we can see a strong arm weapon description, rape, assault with a deadly weapon, aggravated assault, unknown weapon, folding knife, robbery, so on and so forth. All other crimes were worth a standard 1 point. In other words, vandalism or petty theft in a store would be counted as 1 point, whereas murder in a parking lot would be counted as 6. Then, as all of these weighted crime incidents for each parking location are added together, we get the crime indices. Using the numpy interp function, we simply map these resulting crime scores into a range between 0 and 40. Then they are all subtracted from their corresponding safety scores, resulting in the final base form of our safety score. Finally, using the relevant web scraped and pre-processed parking data, we created our Firebase real-time database with the items listed on the slide. Since we had already structured the data as a dictionary, this was a simple task of converting it to a JSON file and using a put request. So this is our Firebase structure. Over here, there's the address divided into different sections, the coordinates for which we used the Google Maps geocoding API, various prices for various days, rates and such, the type, valet, and the same for all the different parking locations that we have in our database. Before the demo, I will give you a brief description of the backend of our app's 3 core functionalities. The first functionality addresses the standard situation of when a driver is looking for the most suitable parking spot for them. For this, the parking list function is used. In the Google Drive folder, this can be found in the functionality 3 script. I apologize for the confusion. I named them in the order I coded it. So the user's address is used for the required input parameters. They can also set various filtering conditions as well as sort by duration, distance, or by the default safety. Based on the set conditions, the locations queried from the Firebase are filtered and then sorted. For duration and distance, Google Maps Distance Matrix API is used. A data frame with the rows of the matched parking locations is then outputted. It is worth noting that since real-time Firebase doesn't support multiple order by conditions, the majority of the filtering needs to be done locally. To maximize our Firebase querying efficiency, we need to minimize the number of location items that are returned each time. So as shown on the left, I identified and ranked the filtering conditions based on how many parking locations each returns, such as if the valet equals true, returns 24, parking type is equals lot, returns 37 locations, and so on. I accordingly wrote the if-elif block on the right for executing the Firebase GET request, such that always the smallest number of locations will be processed locally. The second functionality is executed with the location description function. It gives the current parking details for the specifically searched location. It can be executed in one of 2 ways, either by passing the exact parking ID or an approximate address of the user's desired parking. Before the parking information is outputted, the base safety score is updated using the real-time citizen incidents. We created an email dedicated to receiving these alerts. We parsed the emails and selected only those that occurred within 12 hours of our user's query and are within half a mile from the parking location. We also use these keywords to ignore incidents that don't affect the safety of the user. So over here is our email address. These are the various alerts. So for example, we would not want to consider these ones: search for a missing girl, search for a missing girl, and so on. The more relevant ones for us would be things with keywords like police chase, and so on. So things like search for a missing girl, again, would be ignored, whereas police pursuing burglary suspect or man stabbed would be included. That's what the keywords would be used for. Then we weight these incidents according to recency, as shown on the bottom right. Last, we offer Waze-like functionality for a user to update availability information. This gets executed using the parking location ID and the user's stated occupancy status as the input parameters. As can be seen in the screenshot on the upper right, a patch request is used to update the Firebase data. The availability key's value is changed to the new user input and an update time is added. We also have an additional daily reset function. This function is independent of user interaction. It is updated daily. It is executed daily at midnight, which can be accomplished using a scheduler like cron job. It simply resets all availability data to the default values. This is needed since most parking locations do not allow overnight parking, so availability information that is based on a day-old update will often be misleading. Overall, our goal is to have our users be as well informed as possible. So using the safety score and current crime notices from citizen, drivers can hopefully avoid risk when parking. If this app becomes popular, another positive consequence could be that managers of parking lots with low scores may be prompted to improve safety conditions due to supply and demand. Now we will show you the demo of our Park It Safe and Simple app, implementing all the aforementioned content.
Hello, my name is Alexander Chavez, and I'll be introducing the UI portion of Park It Safe and Simple, which I developed using a Streamlit library in Python. So when users first load up our application, they're presented with Park It's homepage by default. This page contains a mission statement for our application, which to summarize details our goals of providing utility and safety for drivers. Below the statement, we also include a description of the areas of operation for the application, along with a geographic visualization of zip codes that we collected our data from. And below this, finally, we provide descriptions on the three main functionalities that Park It provides, which we will go in depth on while we explore the app. The first two functionalities, specific parking information and availability updates, are located on the second page of Park It. Users can navigate to this page, as well as other pages, by looking at the navigation pane on the left of the interface, which provides a radio widget users can click on. So we'll click on the second one, or option in this case, to navigate to the appropriate page. And if the user wants to hide this pane, they can click on the X icon in the upper right-hand corner, and it will hide the pane. So the current page we're on is mainly dedicated towards drivers who are already familiar with a parking location or who are looking for the nearest parking spot to a given address. In the first scenario, we'll assume that the users already know both the address and type. We will then present a case in which the user instead wants to input an address they want to find parking at without knowing the exact type of it, though. So users will first fill out the form, and for the first user, or scenario in this case, they're looking for the nearest parking spot to the address 6560 Sunset Boulevard, Los Angeles, California, with a zip code of 9028028. And then the user will notify the application that they want to specify a type by clicking yes. They'll specify the type as a lot, but there's also other options for street parking and garage as well. And once they've finished filling out the form, they'll click on the search button, and they'll be notified with a please wait icon that their search has commenced. And then once the query is complete, the icon disappears, and the specific parking information for the matching spot is displayed. For this search, the location returned was Tops Auto Park. And below this section for its name and address, there's also additional information that we provide, including the type of the parking, which the user did specify as lot, whether or not it offers valet, its capacity, its availability, which in this case is available, when this was last updated by users. And furthermore, we also offer a safety score, a list of recent incidents at the location if they occurred in the past 24 hours, And we also take that into account before calculating the safety score and displaying it. Finally, if there are any hourly rates or flat fee parking, they're displayed to the users along with the hours of operation. So below the information displayed, users are offered two options on how to proceed. They can either clear the query search, or they can update the availability of their location. In the case of the latter, this would be utilized once the user visits the parking location and sees that the availability of parking spaces does not match what is recorded in the database for the location. At the moment, Topps Auto Park is closed, but we'll assume that it is open and the user decides to go and visit it. And once they visit it, they see that there are no spots available. So in order to update this in real time for other users, they would click on this second checkbox below, which would update the availability and provide them the drop-down menu from which they can select the exact availability value. They can input it as either being available or occupied. For the user, they know it's occupied in real time, so they'll select occupied. And then once it's finished updating, they'll be notified of this, and they'll be able to click the query result and begin a new search if they would desire to. For this user, they want to verify that those changes have been made to the availability attribute of the location. So what they can do is resubmit their search and then wait for the parking information to load for the specific location, go to the availability section, and they can now see that it's been changed from no space available, from space available to no space available. And so this will also be updated for other users in real time so that this particular user can help out others in avoiding wasting gasoline and time to by driving to parking spots that are already full. We then clear the query result and move on to the other user scenario. And so this user scenario that we're about to look at involves a user who has the same exact address as the previous one, but does not know the type or does not wish to specify. Therefore, they'll change the specific parking type from saying yes to offering to now not offering it. And they'll click the search button. So when this occurs, the search is going to return the closest parking location to the address specified. And in this case, it's a different location given that there is no requirement for typing. And now for this location, given that it's open, you can also see the hourly parking rates and the format in which it's presented to the user. First, the parking price, and as well as the hours. And for this location, you can also see that similar to Topps Auto Park, there's the same incident that was listed under the Topps safety score as there is for this location. This is because both of these locations are within close proximity to the address that the user entered for themselves, which was the same in both occasions. Therefore, they display similar incident reports. So finally, we'll click the clear query result. And once this query result clears, we will move on to the final page and display its functionality as a page in which users can locate parking near the location. Move on to the locate nearby parking page by selecting it in the navigation pane. And now users are presented with a similar form as the previous page, except that this page is meant for the user's exact location to be entered. In addition to the address form, there are also various filters the user can apply to their search to get a parking location that best fits their criteria. Displaying the full functionality of this page, we perform two separate queries. The first query will represent the preferences of a driver who's concerned about convenience, such as proximity and no restrictions. Now, on the other hand, a second query will fill in preferences that match those of a user concerned about safety above all other factors. So we'll begin by entering the same address for both. So 6735 Yucca Street in Los Angeles, California. The zip code of 90028. And so for this user, given that they want to find the most convenient parking locations to park at, they won't specify a type of parking, given that any parking that's convenient will be fine. They won't have any preferences for a valet, but they'll at least require a safety score 50 or higher, and users can manually enter this or click the plus or minus buttons to increment it by 1. And the user will also click the checkbox to only include parking locations that do not have any restrictions, so that only ones that are shown are the ones that are most convenient and easy to park at. And finally, the user can sort their locations that they return from the search by safety, distance, or duration. And this user will decide to sort their locations by distance. And the user can also decide how many locations they want to return in the query. So for now, we'll select only 5. And by default, the first 5 locations are returned anyways. So we'll stick with 5 for now and click the search button. And so depending on the filters of the user, it may take longer for the results to load. But in general, though, for users, given that they're performing one search at a time and have already predefined or predetermined set of preferences in mind, these query searches should be faster, especially if they're only utilizing the functionality of, for example, the locate nearby parking page versus the specific parking information and availability updates page. Using one page will allow the application to run much faster than it does if what we're doing right now in the current demo. So while it may seem that the application does take a while to load, for an average user who's using this application, it will be much faster given that they already have an idea of what they want to do and will only utilize one page and perform at most around 2 searches. So when the user's results are finally loaded, they're notified there have been matches found for what they searched up. And the first thing they're presented with is an interactive map, the scatter plot style. This map plots the user's location in green and the parking locations returned in red. And users can interact with the map by dragging it and zooming in to get a better location of where the parking spots are relative to them. Below this, there's also an interactive table containing locations returned by the user search, displaying attributes such as address, duration, distance, and safety score. In addition to this, there's also an ID column, which represents the location's position in our database. So once the user decides that a specific location in the table is of interest to them, but they still would like to find more information, they are notified below that they can use the ID value of that location to find more specific parking information, which includes its pricing and hours. So users can interact with this table and view the entire table in a much better format by clicking on the expand button next to it. And then they'll locate the ID. So in this case, the user who wants to find the closest location and just wants convenient parking will select the first one, given that it's sorted by distance already. It will select 121. And then in the drop-down menu, they'll be presented with a set list of index values, which only match the ones found in the table above. And they'll select 121, given that that is their preference. And this will load the functionality and send a request to the backend to retrieve the specific parking information for that location using the index in Firebase. So the user will be notified that search is in progress once it begins. And once it finishes, there will be displayed the parking information for that location, along with additional information on rates and hours and any incidents. So in this example, we'll assume that a user decides that a parking spot doesn't really meet their criteria, even though the filters have somewhat filtered out parking spots they would not be interested in. Looking at the parking price, for example, or let's say the hours, we find that the user does not think or believe that these hours and prices really meet their preferences at the moment. Let's say they want hours that are longer or prices that are cheaper. So what a user can do, they want to view other results here that may potentially match what they had in mind. They can go back to the index drop-down menu, click X on the number that they selected as an index to view. Wait for the page to load. Again, this might take a while, depending on the user's filtering criteria. But once it's finished, they can then click on another index if they so desire to view the location for that other parking spot. So in this case, 128, which is the ID of the second closest location to the user, will be selected. And then the specific parking information for that location will also be returned. And then for this user, once they finish looking through the information, they'll also decide to clear the query result for the search. And we're assuming the user does this because we want to perform another search now for a different user. There's different preferences in mind. So the new search we're about to commence will resemble a user that prioritizes safety above other factors, which Parquet supports through its filtering options. And for the sake of simplicity, we'll keep the address the same, but we'll tweak the filter so that locations are selected based on how safe they are, rather than their proximity. So eventually, now the user can clear the query result, and we'll change these filtering options to match a user who cares about safety. So a user who prioritizes safety might potentially want parking locations that are not on the street to prevent any potential accidents that could occur with other cars or any vandalism. They'll also probably want a valet because an attendant there will ensure that the parking location has somewhat of a surveillance aspect or feature to it, so that if anything occurs, the valet can notify the user, or at least the valet can deter anything from happening. And we'll say that this user is much more strict in their safety score, and they'll at least want a 75 for any locations that they're considering. However, because they consider safety to be the most important aspect, they'll also be fine with any restrictions in case, as long as safety is prioritized. And they'll sort the results by safety, limit the search to 5, and then click the search button. Matches will be found in the database depending on their filters. And in this case, there were matches found, they're notified of it. And now a different map appears with different locations for a user concerned about safety over here. And the table below lists all these locations. And the user does not have to sort by safety as it's already been done. And they'll be able to see that the first location has a safety score of 89, is 6 minutes away, and only would take driving 1 mile to get there. It is of lot type garage. So if the user decides that the garage type is much safer than, let's say, a lot type, they'll first start by looking at the specific parking information for that first location, which will be indexed by 73, as it's stated in the table. They'll look for specific parking information by sending a request to the backend, which will then return the parking information. So in this case, the safety score is 84. And similar to other locations, that same robbery at the FedEx shipping center happened nearby on the same day. And so if the user decides that that is okay, given that it has such a high safety score, there's a valet, and it's in the garage, they can then decide to park here and look at the hourly rates for hours and pricing for other information. And this is how a user who prioritizes safety would most likely format their search and filters. And again, because we not only want to help users find parking locations that are nearby and are convenient for them to park in, but we also want to allow users to feel safe when parking, given that so many crimes and incidents occur not only to the car itself, but also to the user. Yeah, but once the user finishes doing that, they'll create a query result, which will then conclude our demo of the Parquet Safe Simple app and its functionality. And thank you for watching.